welcome to lecture 4 of this series. And I thought we would begin this one by taking a brief recap of what we've seen so far, because we've looked at something rather varied and we've got into a lot of detailed proofs, and I think it's good to take a little step back and see what we have achieved. So we've seen 3 quite different models of computation, which give rise to, in some sense, the same class of problems. One is fixed point logic with counting, which we call FPC. Second was polynomial time relational machines, which we looked at a bit briefly in the lectures. And the third was P-uniform symmetric circuits, I should say, with threshold gates. Okay, so one in terms of machines operating on relational structures, one in terms of logic, one in terms of symmetric circuits, and they all give you exactly the same thing, which suggests that we have a robust model of efficient symmetric computation. We can think of FPC as a complexity class inside P, properly inside P, but which is very robustly defined and captures what it means to, in some sense, compute symmetrically inside P. Symmetrically in exactly the sense that arises when you compile computations from high-level specifications which are done at the level of abstract relational structures like graphs. We've also seen that bijection games provide a method for proving lower bounds for this model. Okay, so we have a means of showing undefinability or inexpressibility or lower bounds. The kind of best way of phrasing this depends upon which of the models you're looking at, but bijection games provide a method for proving such lower bounds. And the key is that any class decided in this model has bounded counting width. In other words, it is characterized by a bound on, if you will, the number of variables in counting logic, or the Weisweiler-Lehmann dimension. There are many different characterizations of this, but that's the key. And what I'm going to do in this lecture is relate this to a fourth, rather different again, model of computation, which is also fairly natural. The relationship is not as tight as with those 3. But I'll explain. The essential difference is one of uniformity. For each of these, there is, if you will, okay, this was P-uniform symmetric circuits. We could replace P-uniform by just saying polynomial size, and we get to a sort of non-uniform circuit model, which, as we said, can express even undecidable properties, but this still has the property that everything expressible has bounded counting width. FPC has a corresponding non-uniform version as well. It's the infinitary logic with counting. We haven't really looked at that closely in this course, but that's sort of the non-uniform version. With relational machines, it's a bit trickier because here the uniformity is built into the fact that you have a single machine, a single program that does it, but you can non-uniformize it to get it to get an equivalent model. We're now going to look at a fourth one, which is also inherently non-uniform, like the non-uniform circuit model, and related to this. And this one is based on linear programming. So let's start by having a brief look at what linear programming is. Now, linear programming is a very widely used algorithmic tool for solving optimization problems, right? In fact, it is probably the most commonly used when you have combinatorial optimization problems. It's one of the most commonly used tools out there in practice. We know that linear programming problems can be solved in polynomial time. This was first proved by Kacyan back in 1980 using what's called the ellipsoid method, of which I will give a brief overview later. In practice, the simplex method, which is not provably polynomial time, it's worst case exponential, but in practice it provides very good solutions. The ellipsoid method is not that practical, but more efficient, more practical, and provably polynomial time methods followed, like Karmarkar's interior point method. By now, it's well established that we can solve linear programming problems in polynomial time. So what is a linear programming problem? It's given by a collection of constraints over a set of variables. Now, typically when these problems are described, we think of these variables as ranging over the real numbers. For us, it's more convenient to think of them as ranging over the rational numbers, and we'll see why. But in practice, this makes no difference, because in actual computations, you always represent reals by a rational approximation. So what is a constraint? We usually think of a constraint as something like this. It is a linear combination of the variables x1 to xn, and we bound it by some value b. So we say this linear combination of the variables, so x1 through xn are variables in V, and we're saying this linear combination is less than or equal to b. That's what a constraint looks like. More formally, the constraint is specified by a vector of rational coefficients indexed by the variables v, and what we consider the right-hand side, some constant q. So that's what a linear program is. It is just a collection of constraints like this, where each constraint consists of a vector and a constant. And what is the problem? We can think of this as a decision problem, which is what we call the feasibility problem, is to determine if there is a rational vector which satisfies all the constraints simultaneously. So to satisfy a constraint means exactly this, that you take the product of this vector x with the vector of coefficients. You take the inner product, so the T is for transpose, right? And that should be bounded by the right-hand side of the constraint. So the feasibility problem is a decision problem. It gives you a yes or no answer. More generally, we usually are looking at optimization problems, and there, in addition to the constraints, we're also given an objective function, which is again a linear function, so it's given by a vector of coefficients. And the problem then is to find a feasible point. What a feasible point means exactly this, a vector satisfying all the constraints. But you want to find one at which the objective function is maximized. Okay, that's what we call the optimization problem. So that's what linear programming is for us. Now, why, back in the 1980s, when it was first discovered that linear programming could be done in polynomial time, there was a great deal of excitement because, as I said, it's a very commonly used tool for solving optimization problems. And people thought that perhaps you could actually code hard problems, NP-hard problems, into linear programs, and that this might provide a route even to showing that P equals NP. So people proposed, as I said, for example, you can express the traveling salesman problem as a linear program. Does that mean you can solve it in polynomial time? Well, Yannakakis proved in 1991, sort of settling this kind of argument, that any encoding of the traveling salesman problem as a linear program which satisfies certain natural symmetry conditions must have exponential size. So now we can look at this as a lower bound on a certain model of computation. We're thinking of linear programs as a model of computations, satisfying certain natural symmetry conditions. And I want to try and relate this to the symmetric models of computation we've been talking about. This is not quite the same thing, but there is a relationship, and I want to explore this. This doesn't completely settle the question of whether you can use linear programs to settle the P versus NP question, because the P versus NP question is still unsettled. And if P equals NP, then in fact you can code traveling salesman program. You can reduce it to linear programming, because linear programming is complete for P, it turns out. But by Yannakakis' proof, you cannot do it satisfying certain natural symmetry conditions. And what he argued was that any natural representation of the traveling salesman problem, anything you could think of, would necessarily be symmetric. Okay. So how is the traveling salesman problem a linear program? Well, let's start first of all by defining the problem itself. The problem is we're given a set V of vertices. We call them n vertices. Okay, so n is a number of vertices. And we are given a distance matrix. What is a distance matrix? It is a matrix of rational numbers indexed by V cross V. In fact, I should assume that these are all non-negative rational numbers. So that's the input to the problem. And what we're asked to find is this value. It's the minimum over all bijections between V and the numbers 1 through n. So think of this as linear orders of V. So the minimum over all ways of ordering V, right? There are n factorial such ways of ordering V, of this sum. This is, in the distance matrix, the cost of going from the ith element of V to the I plus 1th element in this particular ordering, summed over all values of n. Sorry, this should be up to n minus 1. And then the cost of going from the last back to the first to complete the cycle, right? So this is the cost, the minimum cost of visiting all the vertices in some order. So we want to now formulate this as a linear optimization problem. So let's introduce a set of variables, xij, for each I and j in V. Okay. So think of this as we did something similar when we were looking at how to input a graph to a circuit. We thought of each Boolean input as being, as each potential edge as a Boolean variable, xij. So we think of a graph as a function from the set x to 0, 1. Right? This is exactly what we did, again, when we were looking at graphs as inputs to circuits. Take those graphs, which are simple cycles of length n. Okay? Each such graph is a function from x to 0, 1. Okay? So we can think of it as a vector of zeros and ones indexed by x. There are, in fact, n minus 1 factorial such simple cycles, right? Because you can order the numbers 1 through n. Any ordering gives you a cycle, except because you could start the cycle at any point. You've counted every cycle n times when you take the n factorial different orders. So there are n minus 1 factorial different simple cycles. So this is a set of n minus 1 factorial vectors, 0, 1 vectors. Now I'm going to consider the convex hull of this. So I'm thinking of these vectors, right? Let me go back a bit. I said this was a collection of 0, 1 vectors indexed by x, but I can think of each vector as a point in Euclidean space. In other words, each element of P is a point in the space, or the vector space of rationals indexed by coordinates in x. And I take the convex hull of these points, that is, in other words, the set of all rational vectors, which can be expressed as combinations of vectors in P, where the coefficients are all non-negative and add up to 1, right? Those are the convex combinations of vectors in P. This defines, in fact, a closed polyhedron inside this Euclidean space. Okay. And what we're saying is, what is the traveling salesman problem? The traveling salesman problem is the problem of minimizing this linear function of the variables xij, right? So Cij, now remember, is the entry, the ijth entry in the distance matrix, which is the input to my traveling salesman problem. So I turn that input into this objective function, and my aim is to minimize this objective function for all vectors x which satisfy it's over all x which are in P, right? This is just a restatement of the traveling salesman problem. I haven't quite got it as a linear combination yet, as a linear program yet. To turn it into a linear program, I replace this condition of minimizing over vectors which are in P to minimizing over vectors which are in the convex hull of P. And now this is clearly a linear program. I have an objective function I'm minimizing. When I defined linear programs, I said we have an objective function we maximize. This is easily turned into that by just negating the function. So, but we want to find the minimum cost over all vectors x which are in the convex hull of P. But the convex hull of P, because any convex polyhedron in Euclidean space can be described as a collection of linear constraints. Okay? So, traveling salesman problem is a linear program, can be expressed as a linear program. Why doesn't this give us a polynomial time algorithm? Well, the point is, of course, that this thing, to describe it by a collection of linear constraints, it is a polyhedron. We can describe it by a collection of linear constraints, but the number of constraints we need is exponential in n, the number of vertices, right? So the thing is, this has exponentially many facets. So it's a polyhedron, so a facet is, the hyperplane which describes one face of it. In fact, we don't even have any explicit description of all the facets of the traveling of this thing that's known as the TSP polytope, right? We know it's the convex hull of a collection of points of n minus 1 factorial points in this space. But how do you describe the actual hyperplanes that make up the facets? No one's ever given an explicit description of this. Okay. That sort of, the direct attempt to encode traveling salesman problem as a linear programming problem leads to this exponential blow up. But that's not what people were trying to do. There's a more subtle way of turning it into a linear program. And that is, instead of trying to describe the convex hull of P, the TSP polytope, directly, right? Explicitly give all its facets, which we know you can't. Could it be obtained as the projection of a polytope of higher dimension, but which has a smaller number of facets? Now, this is sort of a fascinating thing. I'll leave as an exercise. You can construct polytopes in Euclidean space of a small number of dimensions whose projection onto lower dimensions has a greater number of facets. So think of it, try and do this just in 3 dimensions. Think of a 3-dimensional object, which is a polyhedron, right? Whose shadow, the shadow it casts in 2 dimensions, has a number of edges, which is more than the number of faces of the polyhedron. Okay. That's an exercise. So, formally speaking, we ask, is there a Q, a polytope, in this higher dimensional Euclidean space, right, with dimensions x, coordinates x and y. X and y are both sets, which is small in the sense of the number of facets is polynomial in the size of x, but such that the convex hull of P, the polytope we're really interested in, can be obtained as the projection, namely as a set of those vectors in Qx, such that there is some y in Qy, so that the pair xy is in Q. Okay, that's what it means to obtain this conv P as a projection of a polytope with a small number of facets. If you could come up with a description of such a Q in time polynomial in n, then P equals NP, right? Because we'd have a polynomial time algorithm for solving the traveling salesman problem. Namely, you would, given your instance of size n, construct such a Q, and then optimize the function, your objective function given by your input instance over Q instead. And that's now a polynomial size linear program. You can solve it in polynomial time and get your answer to your original traveling salesman problem instance. So that's the question. A weaker condition, instead of saying that Q could be obtained in polynomial time, would simply be to say that such a Q exists and it's of polynomial size, even if we don't know how to compute it. That would still show that NP is in P/poly. Because if you have such a polynomial size instance, you can turn it into a circuit which determines traveling salesman problem of polynomial size. It's just it would be a non-uniform one. So this is the non-uniform model that I was talking about of linear programs. They're called extended formulations. I've talked about the traveling salesman problem. You can easily do it also, instead of optimization, talk about feasibility. And for instance, you can add inequalities for you're given a graph G, and suppose you have a description of what I call the TSP polytope, right? So something which projects down to, remember, the points, the convex hull of the points which give you simple cycles. Then given an input graph, instead of adding an objective function, you simply add these constraints, right? For any variable x, you say its value is less than g of x. So g of x is either 0 or 1. Adding that to Q gives you a polytope which will be empty if the graph G contains no Hamiltonian cycle, but it will be non-empty if it contains a Hamiltonian cycle. So simply solving the linear programming feasibility problem for QG determines whether the graph has a Hamiltonian cycle. Okay, I'll leave you to verify the details of this. So what did Yannakakis prove? So Yannakakis defines a notion of symmetric polytopes. So when this polytope Q that we're looking for is symmetric, whenever you take a permutation pi of SV, now remember V is the collection of vertices, and X is the set of variables Xij, where I and J are in V. Okay, so if you take any permutation of the vertices for instance, your graph, then you can find a permutation of the new extension variables Y with the property that if you apply the permutation pi to the variables X, and here we mean exactly as we did in the case of circuits, you extend the action of pi to pairs V cross V, and hence to the whole vector space Qx. Then we can find a permutation of the variables Y such that applying this pair of permutations to Qx, Qy gives back the original polytope. So note, this looks very much like the symmetry condition we had for circuits, which was that if you apply any permutation to the vertices of the input graph, you can find a permutation on the gates of the circuit so that the whole thing fixes the shape of the circuit. Here, instead of a circuit, we have a polytope, but the symmetry condition is very much the same. Okay, so the action of pi extends to V cross V and hence to this vector space. Similarly, We extend the permutation on the variables y to the vector space Qy. And Yannakakis' theorem says that if you take any symmetric Q whose projection on Qx is exactly the convex hull of P, in other words, it is exactly the TSP polytope, then it must have exponentially many facets. You get an exponential lower bound. As I said, we have no explicit description of the facets of conv P or of any, indeed, anything which projects down to it, but we do get an exponential lower bound. And it's worth noting that Yannakakis gets this lower bound from an exponential lower bound for the matching polytope, which is a polytope for which we do have a very explicit description. So what is a matching polytope? Fix a collection of vertices of even size. And again, let x be the collection of variables, x indexed by xij, where I and j belong to V. So indexed by pairs of vertices. Now, take those points of 0, 1 vectors. We can think of any 0, 1 vector indexed by x as a graph on the set of vertices V. We consider those points which are perfect matchings on V. So before, we took those which are simple cycles. Now I consider those points which are perfect matchings. So they're graphs which look like this, right? And this is why this only makes sense when the total number of vertices is even, right? M is those graphs where every vertex has degree 1. Turns out that the convex hull of M has an explicit description, and this was given by Edmonds back in the 60s, and it's given by this collection of linear constraints. We require each x to be non-negative. For every element I in V, we take the sum over all j of xij, and we require it to be 1. Right? This is really like saying the degree of every vertex is exactly 1. And now this is a key condition. For every odd size subset of V, we say that the sum over xij, where I is in S and j is not in S, is greater than or equal to 1. Okay. Think of it, why this is true for all points in M. If you have a perfect matching, if your graph is simply a matching, rather I should say, then if you have an odd sized set of elements, any odd sized set of elements, then there must be at least one edge going out of your set, right? So this is kind of just relaxing that to play to the situation where the variables xij are now continuous, so they don't they're not just 0, 1 valued. But the key point is that Edmonds proves that this defines exactly those vectors in, if you will, q to the that's the rational numbers q to the x, which are in the convex hull of the set of matchings. But note also that the collection of constraints here is exponential in the set of vertices, because we have one constraint here for every odd size subset of V. So this polytope does have exponentially many facets. And what Yannakakis shows is that any symmetric polytope whose projection down to Qx is the convex hull of the matching polytope must have exponentially many facets. Now, it's interesting that this kind of shows that with these symmetric linear programs in this sense, you can't even solve the perfect matching problem with polynomial-sized linear programs, even though we know the perfect matching problem, the existence of a perfect matching, is in P. So as I said, the lower bound on the traveling salesman polytope is obtained by a reduction from the lower bound on the matching polytope. What happens if we drop the condition of symmetry? Well, there's been a long line of work since Yannakakis' original paper looking at relaxing this notion of symmetry which culminated in the result by Rortvos, who shows an exponential lower bound for both the matching and the TSP polytopes, even without the requirement of symmetry. So simply any polytope which projects down to the matching polytope, so what we call an extended formulation of the matching polytope, any such polytope must have exponentially many facets. Okay. I'm going to take a pause here and then return to try and relate these notions of symmetric linear programs to the kinds of models of computation we've been looking at before.